Alright guys, welcome back to another video. Because I know your exams are coming up, I don't really have time to go through mechanisms step by step, but hopefully after today's video of reduction, you would be able to understand the concept a little bit better, and so that we can focus on retrosynthesis during office hours and study sessions. Okay, so today I'm going to talk about the reduction of ketones or aldehydes, basically any double bonded O. So that includes carboxylic acids, esters, into alcohol. So for example, I have PHOME, this ketone right here. What happens is that when I take sodium borohydride in the presence of methanol, I get a secondary alcohol because this was a ketone right here. If I take benzaldehyde, for example, so now this is an H right here, and I use the same reagents, NaBH4, MEOH, I will get, of course, a primary alcohol. But if I use benzoic acid in the presence of NaBH4 and MEOH, that's actually not going to be any reaction because the sodium borohydride is not strong enough to reduce a carboxylic acid or an ester. Same thing if I had this right here. It's also not going to take part in any reaction because, like I said, sodium borohydride not strong enough to to reduce carboxylic acid and ester. So you will see in the next video that I'm going to use lithium aluminum hydride, LiAlH4, commonly known to you guys as LAH, that will reduce these functional groups into their respective alcohols. Okay, so for now, today we're just going to talk about NaBH4 in the presence of methanol. And I'm just going to go ahead and use the same starting material right here to show you guys how this becomes this. So PHOME. And the first thing you want to know is that sodium borohydride is gonna it's gonna dissociate into its respective ions. So of course, boron is our ion of interest here. It's gonna be what reduces my ketone. And take note, like most of the steps in this reaction are all in a concerted way. So you might have to, when you draw your arrow pushing mechanisms, you cannot break the steps. And I will remind you guys as I go along, but pay close attention. Okay, so first thing I'm gonna do is let me color code my hydrogen. So I'm gonna take this hydrogen right here, the one in yellow, and it's gonna attack this pi bond here. Okay, and at the same time, what happens in orange is that once you form your lone pairs, it's gonna attack boron. Which means that in a single step, I'm gonna get this. So nothing changes. Of course, there's gonna be a negative sign here. And then this is gonna be O, PHME. Now, where do you think the hydrogen went? Don't forget to draw. It's gonna be right here. Sometimes they might want to trick you, and instead of giving you NaBH4, they could give you NaBD4. Do you remember what D is? It's just another isotope of hydrogen, deuterium. So in this case right here, D is going to replace the H. course, we're gonna get the D right here. Cool. All right, so now let's just go back to what we had originally. I just want to make that little note because I think it did appear in the problem sets, remember? Yeah, so this is where we left off, and we can continue. Now, this is not all, because we have, well, a big hint for you to know is that every time you see boron right here, you're probably gonna have to do the step multiple times. And we have how many more? 1, 2, 3 more hydrogens to work with, right? So what's gonna happen right now is another molecule of PHOMe, that ketone, is gonna come along and get itself attacked by this hydrogen here, causing the lone pair to form again, repeating itself, going in. Oops, sorry, it's just giving me this product here. H. And from this step on, I'm not going to draw the implicit hydrogens because it's just the same thing. Okay, and then you can either just write repeat 2 times to show that the boron's going to be tetra substituted, or for the sake of just, taking it step by step, I'm going to show you guys the next 2 steps. So again, another ketone molecule comes along. Let's use a different color this time. Let's go with blue. Okay, so then this hydrogen here is going to attack. Lone pair is formed. Then this goes here, which gives me okay, and of course there's one more that comes along. So if you're wondering why I keep using the same molecule, so remember the analogy that I gave you, like when you have a cup of water, you're not just having a single molecule of water, right? It's like a cup is about what, 250 mils? That's like, I don't know how many moles is that, but basically you have a lot of molecules in your reaction mixture. So they come in abundance, and that's why I can pull multiple molecules to come in this concerted mechanism right here. Okay, let's go with this. Attack. Oops. This is gonna go right here. So please be careful when you draw your arrow pushing mechanisms. It has to be clear, and you need to tell your grader exactly what you're pushing, because if you're sloppy, they might take points off. So just take note. Voila. So, like I said again, you could either just go ahead and show your graders from this step, repeat 2 times to show this step, or you could just draw the entire mechanism. It's fine. Either how, you're going to get the full credit. All right, so now, usually at this point, I tend to get stuck, and I start wondering like, oh shoot, what's going to happen next? But don't forget, your reagents exist for a reason. What else have we not used yet? HOMe, right? Or methanol. So methanol is going to come along right here. Methanol. HOMe. Okay, and what's going to happen is that oxygen is going to attack boron, causing this molecule right here, highlight it in blue, to leave, because now this becomes a good leaving group. And take note that at the same time, again, to consider mechanism, this is going to attack the hydrogen here. So you need to show, here, let me just be a bit clearer with my drawing. This one right here. which gives me HO, pH, my phenol, and my methyl. Okay, and then plus B oops. O ME this time. So then, of course, intuition would tell you that this happens 3 more times. 1, 2, 3, to get me my entire mixture of alcohol right here. And that is how we reduce a ketone into a secondary alcohol.